So we are live now. You can see.
Okay. Medha, do you want to take lead?
Yeah.
Yes, Medha, can you take over and introduce Professor Kembhavi, please?
Yeah. So shall we start now?
Yes, please.
Very good morning to all of you. India International Science Festival, IISF 2020, is an annual event jointly organized by Science and Technology related ministries and Department of Government of India and Vigyan Bharati, that is VIBHA. As a part of IISF 2020 outreach program, IITM Pune is organizing a webinar for science popularizing. On behalf of IITM, I welcome you all for today's webinar. Today we have with us Professor Ajit Kembhavi, former director of IUCA, who will be talking on a very interesting topic entitled Albert Einstein, Gravitational Waves and India. Let me first introduce Professor Kembhavi. Professor Ajit Kembhavi is a principal investigator of the Pune Knowledge Cluster, that is PKC. He is a professor emeritus and former Raja Ramana Fellow at the Inter-University Center for Astronomy and Astrophysics, popularly known as IUCA Pune. He was a director of IUCA until August 15. He did his PhD from TIFR Mumbai with Professor Jayant Narlikar and was a postdoctoral fellow at the Institute of Astronomy, Cambridge. Professor Kembhavi is a distinguished astronomer who works on galaxies, quasars, and extragalactic objects. He also works on various areas of high-energy astrophysics, X-ray, and radio pulsars. He has published a large number of research papers and several books in English and Marathi as well. He received the prestigious Mahatma Jyotiba Phule Award given by the government of Maharashtra for the year 2018 for his book. Professor Kembhavi is involved in many international collaborations and for several years been involved with the 30-meter telescope project and the LIGO India projects. He is now on the apex committee of these projects and a member of the LIGO USA Oversight Committee. He also contributed in the field of data-driven science and now is head of a big data project supported by the National Knowledge Network and works on the application of deep learning to astronomy and biology. Professor Kembhavi has been a member of many national and international boards. He is a vice president of the International Astronomical Union and former president of Astronomical Society of India. He is a fellow of Indian Academy of Science and the National Academy of Science, India. With this brief introduction, I invite Professor Kembhavi to present his talk. Over to you, sir. International Science Festival.
It looks like we have some problems with the network. I'm sure he'll be back in a second or two. So please hold on.
Yeah. Yeah. Hello.
Sir, please unmute your mic.
Sorry, your mic is muted, sir. If you can please unmute yourself and also share your screen. Prabhakar, I think he cannot unmute himself. Is there some problem with the setup there?
No, sir.
Yes, sir.
Okay. And now I'm unmuted. Hello?
Yeah, yes, sir.
Hear
We can
me?
hear you. Yes, sir.
Hello?
Yeah, yes, sir. We can hear you.
Hello?
Yes, sir.
sir,
We can
we
hear you
can.
and we can see. Yeah. Yeah. Please, sir.
Hello, sir. If you can hear us, everything is visible and we can hear you very clearly. Hello, sir. We can hear you very clearly and everything is visible. I think you haven't put your headphones on, that's why you cannot hear us.
Okay. I'm a little bit.
Yeah, no, it happens.
Because this is the first time I'm using this system.
Right.
I generally do it with Zoom or.
Okay.
Okay, now let me share the
Yes.
screen again.
Yeah, we can see your screen. If you can just make it full screen and start it.
Great. All right. Is it okay now?
Yes, sir.
Yes,
Yeah.
sir.
All fine. So I'm sorry about that. It always happens. So I'm very happy to be talking at this India International Science Festival. I'm going to tell you a little bit about Albert Einstein, general relativity theory, and gravitational waves, and the participation and contribution of India in this venture. So it might seem a tall order that I'm going to tell you about all these difficult matters in the short time which is available with all of us. But let me see what we can do. So the discovery of gravitational waves, they were actually detected for the very first time in 2015, and it was announced in 2016 in February. It was a very momentous event because they were first predicted by Einstein exactly 100 years before that. So that was in Einstein uh, announced his general theory of relativity in the year 1915, and in 1916 he predicted the existence of gravitational waves. He himself quite did not believe in that prediction, but people uh, uh, worked on it. Einstein himself worked on it, and over the decades, it was established that they are indeed really a prediction of the theory. And then people tried very hard to detect them, and finally succeeded exactly 100 years after the announcement general relativity. And when it was made public, that was 100 years after Einstein had predicted the existence of gravitational waves. So I will be talking to you about these very interesting events. And first, let us consider a one-sentence introduction to Einstein's special theory of relativity and general theory of relativity. So it's very well known, even among the non-scientists, that Albert Einstein was a patent clerk. He had a degree and a diploma, but he could not get a job as a scientist, and so therefore he was working in the patent office in Bern in Switzerland. And during that time, he carried out his own research, and in the year 1905, he published a series of papers, each of which shook the foundations of classical physics. Then the most important of them possibly was his announcement of the special theory of relativity. So in the special theory of relativity, Einstein combined the independent concepts of space and time into a single concept of space-time. And then he also said that the velocity of light is constant, regardless of whether the source or the observer are moving or whatever. Now, these are again very revolutionary predictions. They led to many, many different consequences and established him as one of the great physicists of his time. Now, one of Einstein's theses was that every theory of physics should be consistent with the special theory of relativity. Electromagnetic theory was consistent, but the theory of gravitation, which was known at that time, which was Isaac Newton's theory of gravitation, was not consistent with special theory of relativity. In order to solve that problem, Einstein had to work for 10 years, and in 1915, he announced his general theory of relativity, which took the unified space-time and then which he had space-time of special relativity, related to gravity, and made it and made the space-time a dynamic entity. So, what do you mean by that? So, we always take that space and time as fixed entities. We really don't say that if a bus drives past, or if a plane drives past, or if a planet moves in our vicinity, then the structure of space-time will be affected. But that is exactly what Einstein was saying. So there are two sources of gravitation. One is the usual mass. All of you know that uh, it is massive particles which attract each other in Newton's theory of gravity. So mass, which is the source of gravitation, but then mass is the same as energy in the special theory of relativity. So mass and energy are sources of gravitation. And when these are present, space-time is curved. And it is the curvature of space-time which affects the trajectory of particles. And so the way the particles move in special cases turns out to be the same as they move if you use Newton's theory of gravitation. So this was a completely new concept, and not everybody believed it in the beginning. The equations which give this, because every physical theory is governed by a set of mathematical equations. The equations which correspond to this theory are very difficult. You can see them on the screen now. They look very elegant, they look very simple, but they are extraordinarily difficult 10 equations. And solving them is a very formidable problem. So now, when Einstein gave his theory, he could not find an exact solution of the equation immediately. But what he did was that he made, using approximate forms of the solutions, he made certain predictions. And these three predictions are very, very important. One of them said that there is gravitational redshift. What do you mean by that? It means that if light moves against the force of gravity, meaning that if I shine a torch upwards from the surface of the earth, then the light is moving away from the source of gravitation, then it gets redshifted, meaning that the color of the light becomes redder than it is on the ground. But if a torch is shown from space into the earth, then as the light approaches earth, it becomes bluer. Then he made another very interesting prediction. He said that just like matter is attracted by gravity, light should also be attracted by gravity. And therefore, there should be a bending of a ray of light when it passes close to a large object. So you see here, this reproduction of this page from Einstein's notebooks, and you see this was done in Zurich, and it was done on 14th of October 1913. That was before his theory was completed. So this was just a prediction along the way while he was understanding more and more of the concepts behind the theory. And you see this light ray going here is bent by it. Einstein believed that the effect can just be seen, but it is not going to be important. But look at in the modern times, where this is a very deep picture taken with a very large telescope of a cluster of galaxies. And you can see these galaxies here, which should appear straight, but you see that these are all bent. And that is because of an effect which is known as gravitational lensing, at the basis of which is the bending of light predicted by Einstein. So other prediction that he made was known as the precession of the perihelion of Mercury. Because Mercury is the planet closest to the Sun. In Newton's theory, the planet would be moving along an elliptical orbit, but according to Einstein's theory, the ellipse will keep changing its position in space. You see that the ellipse is precessing from there to there. So these three predictions have all been tested, have all been found to be correct. And then, but then in the modern times, one has got much more accurate tests. And these also, every test which has been made, as I'll mention as I go along, confirms Einstein's 100-year-old theory to even greater precision. So now this is just a slide on Newtonian gravity, where it was given more than 300 years ago by Isaac Newton. And Isaac Newton said that gravity is the universal attraction between bodies. So if I got a body with mass m1 and another body with mass m2, then everybody knows in school that force is equal to minus g m1 m2 by r square, where r is the distance between them. And the minus sign shows that the force between any two particles is always attractive. Now, one of the consequences of Newton's theory, the nature of Newton's theory, is that it is what is called action at a distance. Okay, meaning that if there are two masses which are casting a force on each other, then if I move one slightly, the other particle will move the force immediately. And then an important difference between the two theories is that in Einstein's theory there are gravitational waves, but in Newton's theory there are no gravitational waves. So let's try to understand what do we mean by gravitational waves. Okay, so so let's first see what you mean by wave motion. And everybody is familiar with wave motion in one form or the other. We see it all the time around us. So when you've got a wave, here is just a picture, of an imaginary wave propagating. So you see that let's say that it is propagating in air, let's say that it's propagating in water. Then what would happen is that at any given point, if you remain at one point, you see that the particles of water here are oscillating. They are going up and down, up and down, and up and down. But then you'll also see that while this is down, the other part is up, and while that is up, a further part is down. So the net effect is that while the particles themselves just move up and down, the wave propagates forward. And then the speed with which the wave propagates depends on the properties of the water or the air through which it is moving. Now, here is a wave. You look at the surface of water. If I drop a stone in it, you see these waves all the time. And then here is a wave which passes, which is passing through a spring. So this, of course, is a longitudinal wave, where this is what is known as a transverse wave. And so then, now we are all familiar with the electromagnetic phenomenon. We couldn't live without it. So when I'm sitting in front of my laptop and I'm speaking into a microphone which is hanging on my neck, and then that is converted to electromagnetic waves. These are being carried by the internet to the whole of the country, and you people are intercepting those waves, and then you are listening and seeing me give my talk. So we are entirely dependent upon the electromagnetic field for our day-to-day life. But I mean, people have known about the existence of electricity and magnetism for centuries. But it was in the 19th, at the end of the second half of the 19th century, that James Clerk Maxwell put down, combined together all the information that he had and put on all the equations. The four equations which are known as the Maxwell equations. And one of the predictions of Maxwell, which he made, was that there would be electromagnetic waves. Now, he did not, this prediction was confirmed by Hertz some years later, but James Maxwell was dead by then. So he did not live to see great confirmation predicted. And he had also predicted that these electromagnetic waves will move forward with the speed of light. And therefore, he also said that light is a form of electromagnetic waves. And without these waves, modern society as we know it would have been completely impossible. Now, now you see that here, I'm not trying to explain it to you, but I said that there is a wave equation which follows very simply from Maxwell's equations of the electromagnetic field. Similarly, Einstein was able to show that at least when gravitational fields are weak, then the gravitational field satisfies this equation which you see here in front of my screen. And for those of you who know a little bit of physics and mathematics, it'll be clear that this again is a wave equation. And what is the consequence of this wave equation? Is that, that there must be gravitational waves. So if I shake a particle here, then waves must propagate forward in the gravitational field. So that was a prediction which was made by Einstein. The crazy thing about these waves is that while there are waves in the gravitational field, there are at the same time waves in space-time, because uh, the gravitational field is completely synonymous with the structure of space-time in Albert Einstein's theory. And so what do you mean by that? So let's take a, here is a, let's say that the space-time is flat because there is no mass there to act as the source of gravitation. But here I take a very heavy body, and then when it comes through, you see that the space-time has not got curved. Now, if this body starts shaking up and down, uh, then uh, then the space-time also will begin to shake, in the sense that the waves, that information about the shaking will propagate forward. And it was an amazing prediction of Einstein's theory that the speed of these waves would be the same as the speed of uh, the light. The gravitational waves also will move exactly with the same speed as electromagnetic waves. So, now how do we confirm all this? The problem is that electromagnetic waves are electromagnetic waves are strong. It's completely uh, simple to detect electromagnetic waves, but with the simplest equipment. But the gravitational waves are extraordinarily weak because gravity itself is a very weak interaction. And if that is true, then how do you detect them? Now it turns out that there's an indirect way of saying, of proving that gravitational waves exist. Let's look at what it is. So many of you would have heard of the concept of a neutron star. So when when a very large mass star explodes, it finishes its life, the outer parts are thrown out in a gigantic explosion, which is known as a supernova. But the inner parts of the star, they collapse to form what is known as a neutron star. A neutron star can have a mass very close to the Chandrasekhar limit of about 1.4 times the mass of the sun. And neutron stars, when they are born, have a very, very strong magnetic field, and they're also spinning very rapidly. And because of these effects, these spinning neutron stars emit radiation. Part of that radiation goes along a beam, exactly as like a searchlight beam. And when, if you got a very distant neutron star, and if the beam happens to intersect one of our radio telescopes, like the GMRT telescope close to Pune, then each time the beam intersects, you'll see a flash of radio waves. And therefore, over a period of time, you see pulses of radio waves. And therefore, this object which emits these pulses is known as, which appears to emit these pulses, is known as a radio pulsar. Now, radio pulsars were discovered in the 1960s, but in 1974, two astronomers called Hulse and Taylor. Taylor is the senior astronomer, a very distinguished astronomer, and Hulse was a student. They were carrying out observations with the Arecibo telescope. You must have heard recently, the Arecibo telescope recently was in the news for all the wrong reasons. A very massive part of it fell onto the telescope dish, and the dish has been completely smashed. It was there in all the press and on TV. And they made a very interesting discovery. They discovered a binary system of neutron stars, meaning that in this system, there are two neutron stars, one of which is a pulsar, and each is going around the other. So this is like the Earth going around the sun. So you can imagine one of the neutron stars is sitting at a point, and the other neutron star, which is a pulsar, is going around it. Now, there are two amazing properties that a system like this has. The first property is that because of the movement of these two particles around each other, they are undergoing very large accelerations, and therefore they emit gravitational waves. The gravitational waves are also emitted because of the movement of the Earth around the sun. The point is that the Earth has very low mass compared to the sun, and the distance between them is very large. And therefore, these gravitational waves would be very, very feeble. But what happens here is that, first of all, the neutron stars are very compact objects. They have a radius each of only 10 kilometers. And this system itself is very, very compact, this system of binary stars, two neutron stars. And therefore, very powerful gravitational waves are emitted by this system. Now, the second important property is that one of them is a pulsar. And the period of a pulsar, which can be found from the time the successive pulsations arrive at the Earth, the periods of pulsars are extraordinarily accurate. And they are very constant, very, very constant, and they can be measured very accurately. And therefore, as the pulsar moves around it, one can make very accurate measurements of the properties of a system like this. So, now as I said that this system emits gravitational waves, and here you see a cartoon of the gravitational waves being emitted. The gravitational waves carry energy, and therefore the energy of this system is continuously decreasing. And it follows from the properties of the gravitational field that when the energy of the system decreases, the system contracts, which means that the two neutron stars move closer to each other. And as they move closer and closer, they emit more and more, they prolifically the gravitational waves, and therefore the system goes increasingly fast. Right? So, so you see, this was a beautiful set of measurements which was made by Hulse and Taylor. And later on, you see, the Hulse and Taylor worked in the 1970s, but later on, several other people joined Taylor's group, and you see that the measurements continuing as late as 2005, 2010. And what is the consequence of these measurements? And you see, if Einstein's theory is right, then the measurements must all be spread out on this line that you see going across the figure. And then the dots actually show the measurements made by Hulse and Taylor. So which means that the measurements made on the rate at which the period of the pulsar is increasing are completely in accord with Einstein's theory. You must understand that the error bars associated with each dot, each measurement, are much smaller than the radius of the dot which is shown here. So this is an extraordinarily accurate confirmation that gravitational waves exist. But this does not mean that they have been detected. So just imagine if I tell you very emphatically that electromagnetic waves exist. You'll agree with me. But if you can't detect them, then you would not have been able to use your cell phones. Right? So this is a very big difference between proving that gravitational waves exist and actually being able to detect them. Nevertheless, this was such an important result that Hulse and Taylor got the Nobel Prize in Physics in 1975. Now, this is, you must understand that astronomy is a very small part of physics in the large, and therefore, for an astronomer to get a Nobel Prize is very rare. And in fact, it was Subramaniam Chandrasekhar was among the first a set of three astronomers who were for the very first time given the Nobel Prize. Right. So now I'm going to show you a simulation of what happens uh, when these neutron stars. I told you there's a pair of neutron stars which is just emitting gravitational waves, and therefore the orbit is shrinking. But let's see what happens to. You see that now one of them is a pulsar. The orbit is shrinking. The neutron stars are moving closer and closer together, and they are distorting each other, and then they sort of merge into each other, and what they form uh, is a black hole, right? And then you see that the space-time around it is horribly disturbed, and as the black hole forms and settles down, the space-time is you can see that there's a curvature in the space-time. Right, so please understand that this is a simulation wholly based on astrophysical predictions. Now, we see the neutron star binary which are detected by Hulse and Taylor. Now, the question is, are they going to be merging soon? Should we be prepared for this event? No, because they are going to merge after tens of millions of years. So, what we need to do is to try to find the binary which is actually merging. And I'll mention at the end of my talk how that could happen, that can happen. So this is just a aside on what is the frequency of gravitational waves. Now you know what the frequency of electromagnetic waves in terms of wavelengths. So when you listen to Vivid Bharati, for example, that is on that is the FM. If you look at the Bombay radio station, it is broadcasting at 550 meter band, which means that the wavelength of the thing is 550 meters. But you can have the frequencies. So these are all very low frequencies, but you can high frequencies. You can have megahertz frequencies, gigahertz frequencies, terahertz frequencies with correspondingly smaller and smaller wavelengths. In the case of gravitational waves, you can have wavelengths as much as the radius of the universe. And these are waves which are emitted in the very early phase of the universe during what is known as a as a inflationary phase. But when you see the kind of binaries that I have talked to you about so far, then their wavelengths are between 1 hertz, which means that it is about one oscillation per second. It can go from 1 hertz to a few thousand hertz, right? So now I've been talking about gravitational waves. Now the question is, what is the importance of gravitational waves? Why should we be so hung up about detecting gravitational waves? Because the fundamental physics that will arise from the fundamental physics that will be able to establish from detection of gravitational waves is what are the properties of gravitational waves? Is Einstein's theory the correct theory of gravity? Does it apply also when the fields are very strong? For example, two neutron stars are merging with each other. Are do black holes really exist? Do black holes obey the laws of general relativity? And in general, how does matter behave when it is under extraordinary pressures and which has very high density? And then, and the detection of gravitational waves will tell us about stellar mass black holes, massive black holes, gamma ray bursts, how stars collapse, the accelerated expansion of the universe, and so on and so forth. So therefore, it is very important to actually detect gravitational waves. And how would we detect gravitational waves? That is very interesting. So look at what's happening here. Is that there is a gravitational wave which is passing by. So we saw that gravitational waves arise from the orbit of the neutron stars around each other. and I showed you how space-time oscillates there. And let us say that there's a pair of neutron stars like that, or a pair of black holes even, at a very great distance from us, and then the gravitational wave is passing by. So you see that if an electromagnetic wave were passing by, the oscillations will be extremely rapid. But here, they're taking place just at about 1 hertz, that means once a second, because that is the frequency of gravitational waves. And what happens when the gravitational waves pass by? Please remember that gravity is the same as the structure of space-time. So as the gravitational waves pass by, so look at an object. Now I can see, I can see here, for example, I don't know whether you can see it. This is the case of my spectacles, and you see that they've got a certain length. And if a gravitational wave passes by perpendicular to it like this, the length would first decrease and the length would first increase, and that goes on and on until the gravitational wave passes by. So now you'll ask me, if what I'm saying is true, why don't we see all kinds of objects changing the length all the time? The point is that this change in length is ridiculously small. So let's first accept that the length changes and move ahead. So here is a circle of particles, and then there's a gravitational wave going by, and you see that as it goes by, the circle is getting distorted into a first ellipse in the upper direction, then an ellipse sideways, then again an ellipse upper direction, then ellipse sideways. So that is the effect of gravitational waves on a circle of particles. So you can see that it is shown here. So now, how do I make use of this very simple fact? Just imagine that I got this circle here, and I put one mirror here at one point of the circle, another mirror at 90 degrees, and then I pass a laser beam. This mirror splits the laser beam into two parts, and then they're reflected by the mirror and they're combined, then they come here. When this happens, there's a phenomenon with which many of you would be familiar, which is known as interference. And when the interference occurs, then you get a particular pattern. Now, if a gravitational wave passes by, we have seen that the circle is distorted into an ellipse. So therefore, this part of the circle has become an ellipse. And then you see that the distance between the beam splitter and this mirror is more than the distance between the beam splitter and this mirror, which means that the two beams travel unequal lengths, and when they are combined together, then you will find that the interference pattern has changed. This simple fact is used into building what is known as a LIGO detector. What is LIGO? The Laser Interferometric Gravitational Wave Observatory. There are two LIGO detectors which are built in the US, and these are very humongous structures. Then the length of each arm is 4 kilometers. Very powerful lasers are used, and there is extremely high vacuum. And through that high vacuum, the laser beams are traveling. And when a gravitational wave passes by, then the length of the arm changes, and which can be detected. And how much is the change in the length of the arms? That's the most amazingly small change. So let us suppose the fractional change, which means that suppose delta L is the change and L is the original length. I take the ratio delta L by L, which is the fractional change. That is as small as 10 to the minus 18 or 10 to the minus 19. What it means is that this 4 kilometer arm, the change in the length of the arm is much less than the radius of a proton. So that is what you are trying to detect. Right. So here is a real LIGO detector, which is in Hanford, Hanford is in the state of Washington in the US, in the northeast of the US. And you see that these narrow pipes, each of this is 4 kilometers in length. And at the central station, and there are these stations here. And you can see a close-up. You can see the big pipe there. And now here you have got what is called advanced LIGO is already been reached. And so which has got very great sensitivity. Now, LIGO detectors were first built 20 years ago, but they were in an experimental stage. People were not able to detect waves, gravitational waves with them. But finally, in 2015, they succeeded in building what is known as advanced LIGO, which has got 10 times sensitivity of the LIGO, the original LIGO detector. And with that, finally, the announcement of the detection was made in 2016. So this is Dave Rice, who is the executive director of the LIGO labs. So he made the announcement in Washington. And at the same time, this was broadcast live all over the world. And in the Chandrasekhar Auditorium in Ayuka, we had a great event that day. And all the people in India working on gravitational waves and hundreds of reporters were present there. And then they heard the announcement. And Prime Minister Modi sent a tweet congratulating all the scientists for doing this. Now, and what do you mean by gravitational waves were detected? Is that there's a change in the length of the arm. And look at this figure 10 to the minus 21. So that is the ratio of the change. And you can see that the change, that this tiny change could be detected because of the sensitivity of the LIGO detector. And then you see that the frequency is increasing. The waves are moving closer and closer. And why is this happening? You can easily guess the answer. When I showed you that there are two objects moving around each other and emitting gravitational waves, and then as they lose energy, they're moving closer and closer, so they're moving faster and faster, and therefore the frequency of moving around it is much slower, much faster. So you see that, and then this part, the beautiful agreement between Einstein's predictions for this one and the observation, and this particular part here. What has happened is that these are not two neutron stars going around each other. It can be concluded that these are two massive black holes which are going around each other. And then when they merge together, they form a single black hole, and that is ringing down here. You go to a temple and you strike a bell, then you stop striking it, and then the bell keeps vibrating, and gradually the sound keeps decreasing. And that is known as ringing. And this ringing was first predicted in 1970 by Professor C.V. Vishweshwara, who was in the US at the time, but who eventually came to India and worked here. And he has been my mentor and guide during my PhD, along with Professor Talik. So you see that these are in spiral occurring. They are moving close together. They are merged and they have formed a black hole. And this very beautiful waveform here. And what are the masses of the black holes? One had a mass 36 times the mass of the sun, the other had 29 times the mass of the sun. But the merged black hole, the total here is 65, but the merged black hole has a mass only 6 to 10 times mass of the sun. So where did the difference go? The difference was emitted as gravitational waves. And so here is a thing that if you had these two black holes sitting here, then their event horizons would look like this, and the combined black hole would look like this, but bigger than the state of Maharashtra. And I'll show you, I come to the end of my talk, I also come to the end of my time, but this is a very, very accurate representation of the merger of these two black holes, and you can see them moving closer and closer together. So this measurement established many different things. One is that it was a conclusive proof of the existence of black holes. It was the conclusive proof of the existence of binaries of black holes. It was also conclusive proof of the existence of gravitational waves, and it was conclusive proof of the correctness of general relativity. Right, so it's a very important observation. And 3 people got the Nobel Prize of Physics in 2017 for it: Rainer Weiss, Barish, and Thorne, all of whom are very senior people. And then they worked to make the LIGO detector possible, both by analyzing it at the theoretical level and helping set up the observatory. And here are the Indian people who made very major contributions to it. Professor Vishweshwara, I've already mentioned, Professor Sanjeev Dhurandhar of Ayuka, and he worked with Professor Satyaprakash, and they developed some techniques for the detection of gravitational waves for inspiraling binaries. And without those techniques, it would have been far, far more difficult to actually make this detection. And Satyaprakash eventually went to England, and from there he went to the US. He is now a very distinguished professor at the Penn State University. And this is Bala Iyer, who first worked with Visheshwara, and then he worked with French astronomers and gravitational physicists, and then they made again very important contributions to the understanding of gravitational wave sources. Now here is a whole team of people, uh, young people, senior people, young people, all of whom have made contributions to detection of gravitational waves and the establishment of LIGO India, about which I'll talk very briefly now. And so the LIGO India project is to make a LIGO gravitational wave detector in in India. So why do you want a detector in India when there are already two detectors working in the US and there are similar detectors working in Europe? The point here is a baseline, meaning that the longer the baseline, the more distant the detectors are from each other, the better will be the observations, and the closer would be, and you'll be able to say which direction those sources are coming from in the sky much more accurately. So, and why does that happen? So here is a very distorted map of the globe. So here you have got the Hanford Observatory in the US, the LIGO Observatory, and observatories all over. So you'll find that when you have an observatory in India, then the arm is as long as possible. And therefore you get a 39 millisecond difference between the arrival of the gravitational wave at this part and arrival of the gravitational wave at that part. And why is this distance very important? You can look at a map of the sky, and then you are seeing a particular gravitational wave source, and then using the present set of detectors, you can see that uh, these are large ellipses. These give you the point in the sky at which it may be located. So there are large uncertainties. But if you have a detector in India, which is far removed from these detectors, then you see that all the uncertainties have decreased dramatically. And if you know where the source is located in the sky, then you will be able to show, then you can say what kind of an object that source is associated with. The LIGO eventually detected a binary neutron star and the merger of a binary neutron star. So I showed you a movie some time ago saying what happens when neutron stars merge, and then when that happened, so that was a theoretical prediction, but now we actually seen that in action. So the LIGO India partnership, so there will be, IUCA is the promoter, carries the site survey, etc., and human resources development, and then the Institute for Plasma Research in Gandhinagar, and then there is the Raja Ramanna Institute for Advanced Technology in Indore. All of these are working together, and then they are spread through many different Indian universities, ISERs, IITs, and so forth. And then we have our partners on the American side. The American partners provide us with the detector, which is the LIGO advanced LIGO detector, which will be upgraded in India to what is known as the A+ detector. And then the entire vacuum system will be built here in India. And where is it going to be located? It is going to be located at a point where which is a small place called Hingoli, about 100 kilometers from Nanded, 70 kilometers from Nanded. And I've been there recently, and all the recently meaning in the pro-COVID recent times. And then you see here, now you just have a set of pillars here saying LIGO, LIGO, LIGO. And eventually, this will turn into a magnificent observatory which looks like this. Here will be the long 4-kilometer long pipes, and then these are the observatory buildings, and all the detections will be made from here. So this is the end of my talk today, and I had taken you from Albert Einstein's predictions made 100 years ago to the actual detection of gravitational waves, and then I have showed you how important is the contribution that India has made to the detection of gravitational waves, and how India is very proudly setting up the LIGO India detector. Thank you very much.
Thank you, sir, for a very interesting talk. We have many questions. I'll select few of them and then we can discuss.
Yeah.
The first question is by at Chandrasekhar Mahapatra.
Yeah.
The question is space-time a natural reality or a mathematical description of nature?
Yeah, that's a very good question. Now, space and time are realities, right? Because because we move in space, and because of time, we become older. So, in fact, if there was no time, maybe we'd all remain younger for all our life, right? But the point is that space-time is a reality, and what is also real is that space-time are combined together into a single space-time structure, which is unified. And second, that this space-time structure is dynamic. It can be affected by the movement of matter and energy. And all of this has been proven experimentally.
Yeah, yeah.
I should also add
The
to that,
next question,
sorry, I
yeah,
just want to add one sentence to my answer. So I say that mathematics and physics get blurred together. So when I look at the equations, they are to me as real as the waves that you can see really passing through water, for example. Right? So there's no great separation between the two.
yeah. Thank you, sir. The next question I'm taking is by at Rajagopalan K. The precession of elliptical orbit of Mercury could be predicted by Newton's theory of gravity. But Einstein's theory on gravity explained marginal deviation in figure, what you have shown. Sir, did you mean the same thing?
Yes. What happens is that an orbit, if there were just one planet going around the sun, then it would be a perfect ellipse, which would be stationary in space. Now, the fact is that there are other planets, because, for example, there can be a great effect because of the planets Jupiter and Saturn. Okay, there can also be an effect because of the obliquity of the sun, and so on and so forth. And it turns out that the total effect is about 550, I've forgotten the exact number, arc seconds per century. So, which is a very tiny, tiny, tiny effect. But then out of this, everything except 43 arc seconds per century could be uh, could be attributed to known effects. And this calculation was done in the 19th century. Right? But the 43 arc seconds remained completely unexplained. So, and that was the first prediction that Einstein made of his theory. So, if you use general relativity and if you look at the orbit of the planets and you find that there should be that extra 43 arc seconds is automatically explained without any further assumptions. It's a great triumph of Einstein's theory.
Yeah, thank you, sir. The next question is by Shivasai Dikshit. He's asking Chandrasekhar limit is about 1.4 times the mass of our sun. Is this value universal? Also, the mass of the sun is decreasing since it is emitting radiation.
So,
What do you say, sir?
I mean, I should congratulate all the people who are asking questions, because typically the question would be something about black holes. So you are asking extremely pertinent questions, very well thought out questions. So the Chandrasekhar limit is indeed about 1.4 solar masses, and you see that it is approximately equal to h cross c upon g mp raised to 4 by 3 and the whole raised to 3 by 2. So the marvelous fact is that the Chandrasekhar mass can be expressed in terms of atomic constants, fundamental constants of nature. And so which means that it is very well known and is a completely established physical time. Right? Second part of the question was, is the mass of the sun decreasing? Yes. Now, I ask you to do a simple calculation. We know that the sun is emitting at the rate of 4 into 10 to the 33 ergs per second. So just calculate how many grams that is per second. Okay, and then you can calculate, you can take the ratio of that to the mass of the sun, and you'll see that it's just a very small, tiny fraction.
Yeah, yes, sir. The next question I'm taking is by Shreyas Keskar. Why do neutron stars spin about themselves?
Yes. So you see, now if you look at a star like the sun, which is a completely normal star in our galaxy, uh, neither big nor small, neither old nor young, and you will find that it is spinning around itself. Why is it spinning around itself? I mean, this was first discovered by Galileo because he It looked at the movement of sunspots on the surface of the sun. So why is it spinning? Because the sun was formed from a gas. Okay, and then it was formed from a gas, and that gas had a certain amount of spin in it, and that spin got magnified. So all stars will be spinning, all planets are spinning, the moon is spinning. Now, the thing is that if you now take the sun and you compress it from its size of 700,000 kilometers to 10 kilometers size of a neutron star, and the angular momentum will be largely constant, and because you are decreasing the radius, it means that the angular speed increases tremendously. And that is why you can have neutron stars which are spinning as fast as 1,000 times per second. They complete 1,000 rotations per second.
So your voice is not audible at the end.
My voice is not audible?
No,
Yeah.
sorry.
Now it's coming.
Medha, the voice is very clear. I think it was your connection.
Okay.
Okay, fine. So I'll go for the next question. There are many questions actually, so I'm selecting few of them. This question is by Sandeep Jaykumar. Is the LIGO India project aimed only at the detection of gravitational waves? What are the research objectives related to the project?
It is detected, the entire job of LIGO India or any LIGO detector to detect gravitational waves. But the gravitational waves will be coming from many different kinds of sources. There are many properties of the gravitational waves which have to be studied. In fact, I showed you 2 slides on that. Okay, one said that why should we be detecting gravitational waves at such a great cost in, in money and in effort? And then also said that there will be so many different implications of the detection of gravitational waves. So there are many more. I wouldn't like to go into that right now. It's very important.
Okay, fine. So the next question is by at Prasanna Lonkar. Does the dying star lead to a stellar black hole?
Now, you see, a dying star, what a dying star leads to depends upon the mass of the star. If the mass of the star is about less than 8 times the mass of the sun, then it will become a white dwarf. And then the explosion is known as a planetary nebula. For between 8 to about 25 times the mass of the sun, you will get a supernova explosion like the Crab Nebula. And what will be left behind is not a white dwarf, but a neutron star. And why does that happen? That happens because the Chandrasekhar limit is violated by the collapsing cloud. And then if you go beyond 25 solar masses, then the remnant is a black hole. So what you get exactly depends upon the starting mass of the star.
Sorry to interrupt you. Before the next question, sir, can you please put off your screen sharing so we can see your video completely?
You're not. I thought I had done that. Now,
Right. If you can stop sharing the screen through Jitsi. Yes, that's perfect.
I'll do that.
Yes,
Stop sharing.
no, this is fine now. Thank you.
Is it fine now?
Yeah.
Yes.
Yeah. Okay.
Medha, you can continue.
Yeah. The next question is by Prasanna Lonkar. Does the E is equal to mc square equation apply to a black hole?
E is equal to mc square is a universal truth. So it will apply to everything. So I actually pointed out to you that the mass of the 2 black holes which merged together in the first detection was 36 and 36 and 29 solar masses. So the total was 65 solar masses. But when they merged together, what formed was just 62 solar masses, a black hole. So where did the other 3 solar masses go? Because mass is equal to energy. So that went into the emission of gravitational waves. And this is not an empty statement. What happens is that you can calculate the masses of the 2 black holes and the remnant independently of calculating the amount of energy which has reached us. And then from the amount of energy which has reached us, one can conclude the total amount of energy which was emitted. And therefore there are 2 sides to the equation. Both the left and the right hand side can be independently measured, and we can show that they are equal to each other. So you see that I would strongly recommend that those of you who have any background in physics should really read more about this because of the extraordinary beauty of not only the theory, not only the prediction, but also the first measurement.
Yeah. I have a very general question. What is the next step that Indian scientists can take to help with the unknowns? And what are the big unknowns?
So you see that you yourself are a scientist. You are working on a different area, but so how do you do it? So all the time you are thinking about it. All the time uh, you are looking at problems, and then you see you pick something out of them and you work on it. And sometimes you get an ordinarily good result. Sometimes you get an extraordinarily good result. Now, once I asked a similar question, uh, yeah, what are the very good problems in the particular area we are talking about that day? And he said that if I had known that, I would have solved those problems myself. I wouldn't tell you about it. So
Yeah.
you yourself have to be creative. You yourself have to uh, look at the problems, and you're not working in isolation. Right? You're working with your friends
Right.
and your colleagues, and you're reading, and with the internet, you're working with the whole world together. So that is a very interesting process. And sometimes you hit the jackpot, but you have to work very, very hard for it. You can't just go on buying lottery tickets. What you need to do is to hit the jackpot is to keep working harder and harder and harder. With success
Right.
not guaranteed.
Yeah, very correct, sir. Yeah, we have many questions actually. We cannot take all the questions here because of the time constraint.
Yes.
So I request audience to communicate with Professor, and you can get his contact details on the IUCA website as well. And with this, I really appreciate the lecture, and I found it very interesting. And on behalf of IISF and IITM, I request Ms. Shreyasi Devnath, who is a research scholar of IITM, to propose the formal vote of thanks.
We have reached the end of this webinar on Albert Einstein, gravitational waves and India as a part of IISF 2020. I would like to thank Professor Ajit Kembhavi for such an interesting and insightful talk. And I'm sure it has been quite an enriching experience for all the viewers, which is quite evident from the questions which we have received. And I'm sure we will hear more from you in the coming future. And I would also like to thank you for accepting our request and deliver such a talk in such a short notice. On this note, I would like to thank the director IITM and the IT support team for their continuous support towards conducting this webinar. And with this, we conclude the session today. Thank you, everyone, for joining the webinar.
Thank you very much. I really enjoyed the experience.
Thank you. Thank you so much, sir.